Okay, so let's talk about energy stores and transfers. The principle of conservation of energy asserts that in a closed system, the total scalar quantity of energy is constant. That means energy cannot be created or destroyed. It only moves between distinct energy stores via specific transfer pathways. So, how many energy stores are there? Well, it depends on how you conceptualize it, but saying that there are 8 fundamental energy stores is a good start. And these are kinetic, gravitational potential, elastic potential, thermal, chemical, nuclear, electrostatic, and magnetic. The two that I listed first, kinetic energy and gravitational potential energy, are the most important to learn first. The kinetic store is symbolized by E with a little k, E sub k. And it's 1/2 times mass times velocity squared. The ingredients make sense. As for the gravitational potential store, that's symbolized by EP, or sometimes EG, where the P and G are subscripted as well. And that's equal to mass multiplied by the gravitational field strength multiplied by the height. It's energy of weight at a height. As for the elastic potential store, which is symbolized by E, capital E with a little lowercase subscript e, well, that's 1/2 times the spring constant times the extension squared, half ke squared. The thermal store constitutes the internal energy of an object, and it's essentially defined as the sum of the random kinetic and potential energies of its particles. Energy shifts between these stores through 4 mechanisms. It can shift from one store to another mechanically by a force acting over a distance, electrically by work done by moving charges, by heating, due to a temperature gradient, as in one place being hotter than another, or by radiation through the propagation of waves such as light or sound. Practical analysis requires tracking these exchanges. You need to keep track of them. For example, an object projected upward undergoes a mechanical transfer from a source like the chemical store in muscles to its kinetic store. As height increases, this kinetic energy is converted to gravitational potential energy. In an ideal case, the loss in kinetic energy equals the gain in gravitational potential energy. Conversely, a slowing vehicle uses the mechanical work done by frictional forces, where work equals force multiplied by distance, to deplete its kinetic store and transfer energy to the thermal stores of the brakes and surroundings, which is a process called dissipation. An accelerating object uses a force to transfer energy from a chemical store, such as fuel, to its kinetic store. And an object hitting an obstacle undergoes a rapid mechanical transfer from kinetic energy to the thermal store of the deformed material and to radiated acoustic waves. There are some other examples I want to mention. In boiling a kettle, an electrical transfer from the mains moves energy to the thermal store of the heating element. That energy then transfers by heating to the water's thermal store, increasing its internal energy and temperature. A change calculated as energy equals mass multiplied by specific heat capacity multiplied by temperature change. The subsequent phase change requires energy input determined by the specific latent heat of vaporization. Alternatively, winding a spring involves mechanical work to transfer energy into an elastic potential store. When released, that stored energy transfers mechanically to the kinetic store of a propelled object. And finally, you can think of a nuclear power plant which facilitates a transfer from a nuclear store via heating to a thermal store, which is then converted through mechanical and electrical transfers. So that's just thinking about energy stores and energy transfer. Now, let's home in on kinetic energy. Kinetic energy, denoted as E sub k, as mentioned earlier, is the scalar quantity of energy an object possesses strictly due to its motion. It is calculated by the formula Ek equals half mv squared, as stated earlier, half times mass times velocity squared. M represents mass in kilograms and V represents speed in meters per second, and that yields the unit joule, Joule, symbolized by capital J. The formula's quadratic dependence on velocity is its most critical feature. Doubling an object's speed quadruples its kinetic energy. This principle has profound implications. In transport physics, the braking distance required to dissipate this energy is proportional to the kinetic energy and therefore scales with the square of the speed. Consequently, a car traveling at 30 meters per second requires 9 times the work and stopping distance compared to one at 10 meters per second. The same scaling explains ballistics and impact mechanics. A low-mass projectile, like a bullet or micrometeorite, inflicts catastrophic damage because its extreme velocity generates immense kinetic energy, given that energy is proportional to velocity squared. By contrast, a heavy, slow-moving truck can possess an equivalent amount of kinetic energy, but delivers it over a far longer collision duration. A final essential point is that mastery of this formula demands strict adherence to SI units. Inputting mass in grams or speed in kilometers per hour without proper conversion will render the calculated output in joules invalid. So you must convert first. So I mentioned kinetic energy and gravitational potential energy were the most important stores to first know about. So let's move on to gravitational potential energy. Gravitational potential energy, or GPE, is the energy stored within an object due to its vertical position in a gravitational field. This store is quantified by the linear equation EP equals mg h, mass multiplied by the gravitational field strength multiplied by the height of the object, with the standard unit being the joule, as before. Mass is measured in kilograms, height, the vertical displacement, that's measured in meters, and gravitational field strength is approximately 9.8 newtons per kilogram on Earth's surface. This energy store serves as the primary reservoir for any mechanical system involving elevation. For example, in hydroelectric power generation, the gravitational potential energy of water held behind a dam represents the exact upper limit of kinetic energy that can be generated in the turbines below, assuming negligible resistive losses, which is a big assumption, by the way. This principle of conservation, where the loss of potential energy equals the gain in kinetic energy, allows the impact speed of a falling object to be predicted by the formula V equals the square root of 2 times g times h, a result which is independent of the object's mass. Once again, that is V equals root 2gh. V equals root 2gh. Practical analysis focuses on the change in gravitational potential energy. Lifting a 500 kilogram pile driver ram by 2 meters stores roughly 9,800 joules of energy, calculated as 500 times 9.8 times 2. This stored energy is then transferred mechanically to the pile upon impact. A crucial nuance is that moving horizontally within a uniform gravitational field changes no potential energy, as the vertical height remains constant. Okay, well, what about work done? Work done is the mechanistic definition of energy transfer. It occurs specifically when a force causes a displacement, calculated as work equals force multiplied by distance. The formula is W equals F times S, where the force F is measured in newtons and displacement S is measured in meters, with both acting along the same line. The unit of work is the joule, which is defined equivalently as 1 Newton meter. Therefore, the terms work done and energy transferred are interchangeable concepts when calculating system changes. This equivalence dictates practical outcomes. To bring a moving vehicle to a rest, the mechanical work done by the braking force, which is the force of friction, multiplied by the braking distance, must equal the vehicle's initial kinetic energy, calculated as 1/2 times mass times velocity squared. This work transfers the vehicle's energy into the thermal store of the brake pads and discs. Conversely, lifting a 10 kilogram load vertically by 2 meters requires work to be done against gravity with a weight of 100 newtons. The work done is 100 newtons times 2 meters, resulting in 200 joules. This directly increases the object's gravitational potential energy store. In contrast, merely holding the same heavy load stationary involves applying an upward force, but with zero displacement. Here, the distance s equals 0, so physically, zero work is performed despite any physiological exertion. Okay, so what does power mean in physics? Power is the rate of energy transfer, a time derivative concept distinguishing the capacity to do work from the speed at which it is delivered. And it's defined by the equation power equals energy over time, or P equals E over T. Or, equivalently, power equals work over time, or P equals W over T. So, the SI unit for power is watt, spelled W-A-T-T. And therefore, 1 watt is equal to 1 joule per second. The practical distinction between work and power is critical in engineering. Two motors lifting identical 100 kilogram loads vertically by 10 meters perform identical work against gravity because W equals mgh. Therefore, in both cases, 9,800 joules of work was done. But a motor completing the lift in 2 seconds has a power of 4,900 watts, and that's 5 times more powerful than one requiring 10 seconds, which has a power of 980 watts. This relationship actually extends to propulsion mechanics, where power is the product of force and velocity. To maintain a constant velocity against resistive forces like air drag, which scales with speed squared, a vehicle's engine must deliver power proportional to the cube of its speed, explaining why high-speed travel requires exponentially higher power outputs than low-speed cruising. Let's now talk a little bit about energy dissipation and efficiency. Power is defined as the rate of energy transfer, as stated before, and it's a, let's see, oh, beg your pardon, there was just a repeat there. Okay, so let's talk about energy resources. Global energy demand is serviced by two distinct categories of resources: non-renewable and renewable. Non-renewable resources, which exist as finite stocks, include coal, oil, natural gas, and nuclear fuels. Renewable resources, which are replenished on human timescales, encompass biofuel, wind, hydro, electricity, geothermal, tidal, solar, and wave energy. Fossil fuels, like coal, oil, and gas, offer high energy density and provide reliable base load electricity, meaning their supply is consistent and independent of weather conditions, unlike solar, of course. Their primary drawback, however, is combustion, which releases long sequestered carbon as carbon dioxide, and that's a primary driver of the greenhouse effect, and sulfur dioxide, which causes acid rain. Nuclear fission using uranium or plutonium provides immense energy density and zero operational carbon emissions. However, it does require the complex long-term management of radioactive waste and carries the risk of catastrophic facility failure, which is quite exaggerated in the news statistically as well. Nuclear power is very safe overall. In contrast, renewable resources like wind and solar power have minimal direct environmental impact. Their principal limitation is intermittency. Their power generation is unreliable due to dependence on variable weather, which necessitates grid balancing from other sources. This backup can come from rapid response systems like hydroelectricity, which is reliable but geographically constrained to specific landforms like flooded valleys or from traditional fossil fuel plants. Current global trends reflect a decarbonization vector marked by a transition from coal to natural gas, which produces less carbon dioxide per unit of energy, and by the rapid scaling of renewable infrastructure. Nevertheless, the unparalleled energy density and easy transportability of refined oil continue to ensure its dominance within the transportation sector. Some more examples illustrate these dynamics. A natural gas power plant exemplifies a move towards lower carbon fossil fuel use, though it remains a carbon emitter. A large-scale solar farm paired with a grid-scale battery storage system demonstrates one technological solution to renewable intermittency. Meanwhile, the continued development of internal combustion engines underscores the persistent challenge of displacing oil and global transport. Alright, so let's now talk about electricity itself. Let's talk about electricity and electric charge and current. Electric current is symbolized by I, and it's measured in amperes. And it's the rate of flow of electric charge, whose symbol is Q and is measured in coulombs. So, therefore, we have an equation. Q equals IT. Q equals IT, or I prefer I equals Q over T, because that defines current in terms of charge. T is in seconds. As I say, I is in amperes and Q charge is in coulombs. For a current to exist, there must be both a source of potential difference, such as a cell or battery, to do work on the charge carriers, and a complete closed conducting loop. In metallic conductors like copper wire, charge carriers are delocalized electrons, each negatively charged, which physically move from the negative terminal toward the positive terminal. However, by long-standing convention, so-called conventional current is regarded as flowing from positive to negative. It's unfortunate, but it's a consequence of history. This convention remains essential for correctly applying circuit rules, for instance when analyzing diode direction or using Fleming's left-hand rule for motor effect. Charge carriers are not always electrons, though. In ionic systems, such as during the electrolysis of molten sodium chloride within a lead-acid battery or in a hydrogen fuel cell, current consists of moving ions. That's cations moving towards the cathode and anions moving towards the anode. Quantitatively, a current of 1 amp equals a flow of 1 coulomb per second. Since 1 electron carries about 1.6 times 10 to the minus 19 coulombs, 1 amp corresponds to approximately 6.25 times 10 to the 18 electrons passing a given point each second. Crucially, electric charge is conserved. Therefore, in a single closed series loop, the current value is identical at every point. Current is not used up, so to speak, by components. A filament lamp, for example, does not consume current. It converts electrical energy into light and heat, while the same current flows through it and returns to the source. Okay, so what is potential difference? Let's talk about that, or voltage. Potential difference, or voltage, symbolized by V and measured in volts, also symbolized by V, quantifies the work done per unit of charge. So, therefore, you would define V as V equals E over Q, right? And from that, you can derive that E is equal to QV. 1 volt represents the transfer of 1 joule of energy for each coulomb of charge moving between 2 points. This energy transfer is what drives electrical current. In a source such as a 12-volt car battery, chemical energy is converted into electrical potential energy. Across a load, such as a bulb, that stored energy is converted into other forms, like light and heat. To measure this difference in energy between 2 points in a circuit, a voltmeter must be connected in parallel across the component, contrasting with an ammeter, which is connected in series to measure charge flow. This definition underpins practical electrical engineering and safety. A high voltage transmission line may carry a small current, but transfers immense total energy because of the massive work done per coulomb. Consequently, a 230 volt main supply delivers far more energy per coulomb than a 1.5 volt AA cell, requiring components with higher insulation and power ratings. Some more examples illustrate this range, like the 400 volt system in an electric vehicle, which necessitates robust safety systems to manage its high energy per charge, while the 1.2 volts across a microprocessor core requires precise low voltage regulation. And let's finish up here by talking a little bit about resistance. Resistance, symbolized by R and measured in ohms, symbolized by omega, quantifies a component's opposition to electric current. This opposition physically arises from collisions between the material's delocalized electrons and its vibrating ionic lattice. The fundamental relationship is Ohm's law, V equals IR, or equivalently, R equals V over I. This law states that for a given potential difference, current is inversely proportional to resistance. Under identical voltage, a 10 ohm resistor permits 10 times the current of a 100 ohm resistor. The work done to overcome this opposition dissipates electrical energy as heat, a phenomenon known as Joule heating. This effect is harnessed in devices like electric heaters and fusers, but minimized in power transmission cables to avoid energy loss. Resistance is not an inherent constant for all components. It serves as the fixed proportionality constant in ohmic conductors, but varies in non-ohmic devices like diodes. Consequently, practical circuit design strategically manipulates resistance to limit current for protecting components like LEDs, or to divide voltage across different parts of a circuit. Further examples of this manipulation include using a thermistor whose resistance changes with temperature in a temperature sensing circuit, and employing a variable resistor or a potentiometer to manually control current in a dimmer switch. Right, so we'll wrap it up there.